Okay, I think we'll get started. So today we're going to talk about the first of the two non-conservative forces that we'll be most focused with, that is friction. Next time we'll talk about drag, and there's some distinctions between friction and drag, as we'll see as we get through these two videos. So the empirical laws of dry friction, so this is the typical friction that we're most used to. There's two of Hamilton's laws. The first law says that friction is proportional to the load. So whatever load is pushing down against the contact between, say, an object and the surface, or two objects, the friction will be proportional to that load. Typically, it's the normal force, as we'll see, although I suppose there could be different situations. Second law is that, interestingly, and maybe somewhat unintuitively, the friction is independent of the contact surface. And you can kind of intuit that by if you have a smaller contact surface, then the load per area is bigger, and we're proportional to load. And then if we have a bigger contact area, then the load per area is smaller, and it just so happens that that's independent of the area. And the other thing, and this is what distinguishes it from drag, as we'll see next time, is that the force is independent of the sliding velocity if the object is moving. All right, so we will use F here to represent the frictional force. Sometimes we'll use capital F sub friction, but here we'll use the F. And so typically, in a situation like this where we have a mass on, say, a surface, then we could draw the free body diagram for the mass. It will have a weight, and there will be a normal force acting opposite that weight. The force then, the frictional force, will be given to us by the coefficient of friction and the normal force. Now, this is magnitude. The vector is opposing motion. So in this case, where we're sitting just still, the friction is 0. But if we were to tilt this, as we will up here, we'll see that the friction is not 0. Okay. So now the coefficient of friction comes in two forms. Mu s, that's a static friction, and mu k, which is the kinetic friction. So static friction is when there's no motion. So if we were to push on this box, but not push hard enough for it to move, then the box would be pushing back on us, right? And the origin of that would be the friction force opposing the motion. We want to move it this way. The frictional force then will push this way. And if we get on this side of the box and push it this way, then the frictional force will push this way. Now, if we push hard enough to get it moving, then the friction will be given to us by the kinetic coefficient of friction. Now, these are unitless numbers, and they depend on the type of surfaces. So it depends on both materials that are in contact. So, for example, steel on steel would be different than steel on aluminum or steel on copper, etc. All right. Now, as you might have experienced, that once you get something that doesn't want to move because of friction moving, it's a little easier to push it. And that's because the kinetic friction is always less than the static friction. Sometimes a lot less, sometimes just a little bit less. Here are a couple examples. So steel on steel has a static friction of about 0.75 and a kinetic friction of about 0.5. So about 150% more here than here. Or I guess, I mean 50% more, 50% more. Now, this is interesting. This is a neat one. Human cartilage, lubricated. So the fluid that's in the cartilage allows for very little friction as those move across each other, and particularly very low kinetic friction. And so you could see where that would be a huge evolutionary advantage, not just humans, but all animals, for motion. If there's very little friction, every time we move, our cartilages are moving over each other and moving around. And so if that had a lot of friction, we would be wasting a lot of energy. And we would also be heating the tissue pretty significantly as well. So very important that that is very low friction. Okay, so this is all macroscopic friction, and that's what we'll be most concerned with, things that we can hold in our hand. Now, there is an atomic origin, and we won't go into this, at least in these courses. Maybe later in an upper level course in this curriculum we will. Almost surely we will. But at this level, we'll just note that the atomic source of friction is as one surface rubs over another at the atomic level, it induces vibrations in the lattice. And you can kind of imagine like just plucking the lattice as you go along, as it catches and releases, catches and releases. And that gives rise to lattice vibrations, which is essentially heat. And so that's the atomic origin. But we won't worry too much about that. We'll do problems focused mainly on this. All right, so let's look at a case here where we've got this box on this ramp. And note now, we're going to change our coordinate system so that our x-axis is along the ramp here. So this will be our x-axis going this way. And we'll only be sliding then along the ramp. So it's really a one-dimensional problem. But we have to think about it in the two dimensions as we draw the free body diagram. So let's think about a couple of free body diagrams that we could draw. So if there's no friction, we have weight, and then our normal force is always perpendicular to the point of contact. So that's what it means to be a normal force. And so there's going to be a net force off in this direction, right down the ramp. And so the box would accelerate down the ramp. Now, it won't accelerate as much as if it was just dropped, but we'll accelerate down the ramp with this amount of force. And actually, this would be, I think, weight times cosine or sine of 30 here down the ramp. Okay, well now, let's take the other extreme where the box is not moving. Then what do we have to have? Well, we can't have any net force. So here was our force without any friction. So we'd have to have a frictional force this way. Such that these vectors add to 0. And this would be a static friction. So we would be just sitting in place. That's a static friction. Now, let's let the box slide, but slide such that it's moving at constant velocity, or what's called terminal velocity. This will look exactly the same, because if we're moving at uniform motion, the only difference here is that this will be kinetic friction, and it will have no net force, so we'll be moving at a constant velocity. And finally, let's say there isn't enough kinetic friction so that we don't reach our terminal velocity here. That's maybe not the best way to talk about it. We'll talk about terminal velocity more in the context of drag. But what I mean here is we are not reaching the point where we are moving at a constant velocity. And so in which case we might have a small amount of frictional force, our normal force, and our weight force. But it's not enough to allow for no net force here. So this will be our net force. And so we will get some acceleration down the ramp. Not as much as if there was no friction, but there will be some because there's not enough friction to counteract this lopsidedness of force due to the ramp. Okay, well, let's work an actual problem here. And let's connect it to this idea of conservation of energy. Now this is a dissipative system. So whenever we have friction or drag, we are in a non-conservative situation or a dissipative system. And so we expect here that we shouldn't, say, have a sum of kinetic energy and potential energy. But if we expand our system to include the environment, then ultimately, again, we have a conserved system and energy conservation applies. So applied globally, energy conservation is always true. Applied locally to some system, it may be conserved if there's no interaction with the environment, or if the interaction environment is such that there's no net loss of energy to the environment, then it would be conservative. But otherwise, if there's some loss of heat, then or light or sound or whatever, then there is a non-conservative situation, which we would have here because, of course, we're sliding against the surface and we're losing energy into the ramp. Okay, well, let's work through this now carefully. So the weight, we can calculate if it's 10 kilograms, 9.8 meters per second squared for gravity, and so we'd have 98 newtons. Now the normal force is not 98 newtons because not all of the weight is pressing straight down on the surface like it would be over here. And in fact, the normal force is going to be cosine of this angle. And let's check that. If this angle goes down to 0, cosine of 0 is 1, and so then that would indeed equal the weight and counter the weight. So if we had no friction, right, we have this lopsidedness, and we have a net force down the ramp, and so let's calculate that. Well, down the ramp is going to be 90 degrees to the normal. And so there'll be a component of the weight that is in this direction. And that's going to be, we could think of it as either sine 30 or cosine of 60. I guess I used cosine of 60 here. And so that gives us 49 newtons of force down the ramp. So this is if there was no friction. So now let's take the special case where we have just minimal friction. So the box is just moving. Any more friction, the box would be stopped. And any less friction, we would be accelerating. And so in that case, our 49 is equal to our kinetic friction times the normal, right? Because that's our formula for friction. And so we can get our coefficient of friction, and we get 0.58 here, and that's no units on that. So what's happening here is this is the coefficient of friction we would need in order for this box to just slide at a constant rate. Now, let's say we just tap it and it's moving infinitely slowly, right? So we can take it as moving as slow as we want it. Let's see what happens when this gets down to the bottom of this ramp. Well, let's do a little trigonometry here. The height here is 1.5 meters, so this total ramp distance is 3 meters. So let's look at it from two perspectives. Let's look at it from a conservation of energy perspective, and let's look at it as from a work perspective. So the box starts at 5 meters above the ground, or 1.5 meters above the ground, ends up over here, but that doesn't matter, at 0 meters above the ground. And so the total change in kinetic energy is 147 joules. So 10 times 9.8 times 1.5. Now we're moving infinitely slowly, so that means all along the way, our kinetic energy is 0. Right? So we just tap it, just barely moves, kinetic energy is 0. So then our energy has changed by the amount of the change in the potential energy. Well, where did that go? That had to have gone into thermal energy or heat. So we're going to use Q here as heat. Now, there's a lot of Q's running around. We use Q for charge a lot, as we did in the Introduction to Physical Chemistry 1. We won't run into charges as much in Introduction to Physical Chemistry 2, but then we'll see them again in Physical Chemistry 3. So thankfully, we don't often run into charges and heat at the same time too often. So we should be okay notation-wise there. Well, now let's flip this and look at a different perspective and say, how much work was that friction doing as a force? So we know that work is force times distance. So work, let's see, I'll use blue here. Force times the distance, or the displacement. That's for a constant force. It's really the integral of the force, but this is a constant force, so we don't need to worry about that. And so D here is our 3 meters. So there's our D. Here's our force. And if we multiply that, indeed, we get 147 joules. Okay, so is this work or is this heat? Well, it kind of depends on your perspective and what you're really talking about. If we are talking about where does that energy go and in what form is it, then it's heat. So the box slid down. It's at the bottom now. It has less energy than it had before, and that energy went into heating up the ramp and the environment and the air and so on. If we're looking at it from the perspective of the amount of work it takes to lower this box down this ramp, then we can think of it as work. But what we're doing there is we're not really caring where that energy goes, right, or comes from. So in this case, where it goes. All right, so that's it for friction. And again, this is one of the 2 dissipative forces for dissipative systems. Next time we'll talk about drag. Drag has a little bit extra complication. Well, there's 2 cases here, static and kinetic. Drag has 2 situations. One where the drag force is proportional to the velocity squared, and the other where it's proportional to velocity. And so we'll see that's what really distinguishes it is, this last one, that it's independent of velocity. Drag is dependent on velocity. So the forces are kind of coupled together. They're dissipative forces, but they split on whether they depend on velocity or not. And then drag splits into how it depends on velocity. All right, so that's it for friction.